Hi again. Whoops. Don't know if I'm in the right spot here or not on your screen. Hi again. Today I'm coming to you with a lesson about absolute zero. Still talking about states of matter and gas laws, not so much just gas in this lesson. It's called absolute zero, and you see that little picture of thermostat chilly there, kind of like we were this winter, right? Like super crazy chilly. Has everything to do with temperature, this lesson, and absolute zero you can imagine is going to have something to do with a really, really cold temperature. I want you to think about something before I even begin, and that is the kinetic molecular theory. Remember, we said the word kinetic means movement and molecular means molecules. So in the kinetic molecular theory, we're talking about how molecules move, and we've said in general so far, as the pressure or the temperature increases on a sample, then we would expect the molecules to move faster and collide more frequently. That's why we have gases, and that's why we have a lot of gas behavior that we do. We just got done talking about real gases versus ideal gases, and this idea that with an ideal gas, they constantly move. And we did kind of compare and contrast real gases and ideal gases and said sometimes, maybe for an infinitesimal segment, some of these molecules will stop. But think about if the temperature and the pressure determine number of collisions and how fast a group of molecules are moving. I mean, have you thought about, can all the molecules stop moving or come close? Why don't you answer that now? Do you think a sample of water molecules, for example, could just stop moving? The answer is most definitely yes. And what would that require? What we're going to talk about today is everything that would require. It would require very, very, very cold temperatures, right? Because if hot temperatures excite molecules and make them all crazy and bouncing off the walls. I used to use the example of kindergartners on pixie sticks. You know, that would be my nightmare as a teacher, period, that somebody would make me teach kindergarten, number one. And then number two, just hand out, instead of strawberries for snack, maybe like pixie sticks, you know, those little tubes full of sugar. Because then they'd be all wound up and crazy. Sugar doesn't do that to me, but apparently it does it to other people. So in any case, if that's what heat does, then you would assume that cold, this idea of cold temperatures, would do the opposite, would slow them down. It would get them sitting still. So we're going to look at that today and exactly what that requires and what it all is that we're talking about. Let me see here. Sorry, I had to reconfigure for a second. Lesson 11 is about temperature. It's about not only knowing what different temperatures mean and really the true definition of temperature, but also understanding that we also always have to be in kelvins whenever we're talking about any changes of matter or definitely gas laws. We're going to redefine temperature. Temperature you guys probably think of as heat or lack of heat. Today we're going to define it as kinetic energy. We're going to spend some time converting temperatures and just making sure you know what this idea of absolute means. So we're going to revisit this idea again that molecules move constantly and that all of molecular motion produces the properties we've been talking about as gases. We very first started this unit, we talked about like 5 different gas properties. Right? And so far in most of the gas laws, we've described them. The fact that gas volume changes with pressure, gas volume changes with temperature, gas volume is what's the word I'm looking for? Influenced by pressure, and so on. We haven't explored much more about diffusion, but we said gases diffuse. So many of these properties come from the movement of molecules, namely pressure. Pressure is, as we said, generally a measure of the collisions between molecules. Pressure is a force per square unit area, right? So force, if you think about it as like pushing something or applying a force, if I push my mouse along the desktop, that would be force. Right? Some force involved there. Molecules hitting the side of a container or other molecules is a force, so it creates pressure. If we didn't have molecular motion, molecules moving, we wouldn't have collisions because they would just stand still, right? We also get volume from gas movement, gas particle movement. We said gases are primarily made up of empty space. And if we didn't get that movement, we wouldn't get all of the empty space that we do measure and experience and see in our gas samples. And then finally, temperature. What we're going to say here going forward is that temperature is actually a measure, just like pressure is a measure of collisions, temperature is a measure of speed, the amount of kinetic energy of the particles. Kinetic energy, I'm going to just basically redefine here as speed. At some point in your science, you probably have come across it, but kinetic energy is really very strongly a physics term, so this is something you'll go into more detail should you take physics next year. Kinetic energy, I'm just going to sort of say as speed. It's movement. There's two types of energy. We have kinetic, of course, and then we have potential. Potential energy, as the word potential implies, if you have potential in an academic career, if you have potential in your ability to put on makeup or do hair, if you have potential in the field of fixing cars, then you have promise, right? You may not be using it as a career now, utilizing it, making money from it, but you could, and people think you have a skill. So potential energy is energy that's not yet used. Kinetic energy is being used, and we can basically measure that in terms of speed. So I'm just going to ask you to type in the box there. We're going to practice this just a little bit. Who has the greater kinetic energy here? The tortoise or the hare? Now, I'm not asking who wins the race, because we know who wins the race, right? But he doesn't really win the race because he's faster. Who has greater kinetic energy? Of course, it's the bunny. I didn't mean to move the bunny. I just didn't have my pen on. The bunny moves really fast. I have a couple bunnies in my backyard, and when I go out there on my deck and I holler to them, they bounce their little tails away really quick. But if I saw a turtle, he'd be like, whatever. I'm not moving too fast for you. Okay, how about the Hulk or Iron Man? I have not actually seen Avengers, but I have seen the Iron Man movies, and I know what Iron Man does, and I know Hulk from way back in the day when he was on TV. So, which one has a greater kinetic energy there, Hulk or Iron Man? That would be Iron Man. He flies, right? He zips and zoos all over the place. Hulk is pretty big and heavy. He's kind of like a crazy huge giant monster, but he can't get anywhere any too quickly. Okay, and this is a stretch. I've taught classes where students didn't know who these two characters were, and if that's true, I'm sorry for them, and I'm sorry for you. This is Wile E. Coyote, and this is the Roadrunner. Which one of those is faster? Or has more kinetic energy? That would be the Roadrunner. He's really super quick and fast. He runs so fast you can't even see his feet when he's running, right? It just looks like a really fast little windmill. Okay, so hopefully you understand kinetic energy now. We can define temperature. Temperature, no matter what scale you use, whether we're measuring Fahrenheit or Celsius or Kelvin, is a measure of the average kinetic energy in a sample. Average. So what does this mean? It means generally when the temperature is high or increases, and I'm gonna also write in parentheses here, when it's high. When it's hot, temperature increases. Molecules move faster, or they move fast in general. So in the summer, when it's 80, 90 degrees Fahrenheit, the molecules are moving much faster around us than when it's 20 degrees Fahrenheit in our winters here in Pennsylvania. And then conversely, when the temperature decreases or when the temperature is low, the molecules move slowly, markedly much more slowly. My webcam keeps tilting here. Okay. So if that's true, before I do any more explanation on anything, I would like for you to try to answer this question. Okay, if it's true that temperature is a measure of average kinetic energy, then, and I have two substances, A and B. One substance is at 25 degrees C, the other substance is at 5 degrees C. Which one, substance A or B, has the higher average kinetic energy? It's kind of a flip question. Now I'm giving you temperature. I want you to tell me which one is faster. That would be substance A. Substance A is 25 degrees C, and you notice I didn't convert to Kelvin here. It's not necessary. As long as these two guys are in the same units, we're comparing apples to apples, for instance, then we can make a comparison on the size of their number, or the magnitude of the temperature we're referring to here. We didn't have to convert to Kelvin. 25 is bigger than 5. This is, relatively speaking, a high temperature, whereas 5 is relatively a low temperature. And if we say the high temperature molecules move quickly and the low temperature molecules move slowly, then substance A will move more quickly. Okay, let's try our hand at this one. This is a little different because we're comparing temperatures using different units. The question says carbon dioxide, which is formula CO2, has the greatest kinetic energy at which of the following temperatures? 273 K, 50 degrees C, 30 degrees C, or minus 10 degrees C. Take a moment and think about that. Okay, let's see what you logged here. Of course, I gave you the conversion on the right-hand side because we need to compare apples to apples. So you had a couple choices here. You could convert the units of Kelvin, A, to units of Celsius, or you can convert all of these Celsius temperatures to Kelvin and compare them. Let's take this strategy because we're always trying to teach you, I'm always trying to teach you strategies in problem solving from a standardized test point of view. So only one of your options here is Kelvin. We can still look among your 3 Celsius options and say which of those is going to be the greatest kinetic energy. And by the way, we need to know what that means first. Greatest kinetic energy means highest temperature, right? So those two things go hand in hand, highest temp. So we look at our degrees C options and we have 50, 30, and minus 10. Right away, you would say, well, minus 10 is less than 50. So if we were only given these 3 options, minus 10 is not the answer. That's the coldest. And 30 is colder than 50 because 30 is less than 50. So really, our answers end up being between 273K and 50. So it doesn't matter which one of those that we convert. Easier for me, I think, to just add 273. So that's what I'm going to do here. 273 plus 50 works out to be 323 Kelvin. And of course, that's the bigger temperature, the higher temperature. So that would be the hotter substance and the faster molecules. So the correct answer here, 50 degrees C. Okay. We could have also gone the other way. I'll use blue to do the other way. We take our Kelvin temperature and subtract 273. And in this case, this was probably easier to get to degrees Celsius because 273 minus 273 is 0, right? And 0 degrees C kind of ends up somewhere in between here, in between the negatives and the positives. B is the correct answer there. So if you answered that, you're on the road. You're on the road to something good. Now, the title of our lesson, Absolute Zero. As I said, no matter what scale you use, Celsius, Fahrenheit, Kelvin, temperature is a measure of average kinetic energy. There was a scientist, his name was Lord Kelvin, and I think we've mentioned him before. He's the one that the whole Kelvin temperature system is based off of. He imagined a world where molecular motion ceased to exist. Molecules stopped moving. And he suggested that this temperature would be the coldest temperature that could possibly be reached. The absolute temperature, if you will. Absolute kind of means extreme. You know, when you learn in math class, the absolute value Kind of the same thing here. Absolute zero, all motion stops. That's basically a definition you need to know. Absolute zero means the same thing as 0 degrees K. That's the actual number, that's the actual temperature that's assigned to absolute zero. But additionally, you need to know theoretically, conceptually, that absolute zero is the coldest that we could ever reach. In fact, we have never reached. And it's the temperature at which all motion stops. This might make a little bit more sense a few units from now when we talk about phase diagrams and melting and freezing and what happens to the temperature. Even though you guys know from living in the world, we take this glass of water here and we try to freeze it, we have to lower the temperature. So molecule motion tends to slow down as we go from gas to liquid to solid. In any case, how cold is absolute zero? There's a graphic in your course that is quite nice, I think. It compares some temperatures we're familiar with to temperatures we're not so much familiar with, but we can then sort of get a grasp on how cold this really is. Of course, we have water boiling at 100 degrees C. I think that works out to also 202 Fahrenheit. So that's pretty hot, right? We don't want to put our hand in boiling water. That would hurt. Yet, on the inside of us, we are 98, about 98.5, 98, 99 degrees Fahrenheit. So boiling water is like double our temperature. I'm not sure what that is in Celsius, but I'm going to say it's probably around 50 something, because it's about half of the boiling water. And then water freezes at 0 degrees C, or what we know as 32 Fahrenheit. And that's pretty cold, right? 32 degrees Fahrenheit is pretty cold. You see this huge discrepancy, this huge gap between water freezing and some other gases freezing, and this should say O2, N2, and H2. Those are diatomic molecule gases. Oxygen that we breathe freezing. And let's see, I meant to do this. This graph shows molecular motion on the y-axis, where as we go up the axis, molecules are moving faster. As we go down the axis, molecules are moving slower. And temperature, where we go across, we have higher temperatures. When we go to the left, we have lower temperatures. So water boiling, of course, is going to be one of our higher temperatures, and you can see it matches up on the y-axis with a very fast molecular motion. Okay. Body temperature is less than water boiling in terms of its temperature, and it's correspondingly less in molecular motion, how fast it goes. I'm going to say less fast. Water freezing is even lower in temperature and less fast again in terms of molecular motion. When we jump that big chasm between water freezing and oxygen freezing, we see that the temperature has dropped considerably between those two. And accordingly, so has the speed. So I'm going to say much, much less fast when we're looking at oxygen, nitrogen, and hydrogen freezing, and helium. We have no concept of that really. It's so very cold. Okay, so that's sort of the basis of, you want to be able to identify, answer questions about kinetic energy, movement of molecules, and how it relates to that term temperature. We shouldn't necessarily think of temperature as heat or a measure of hotness, but now we need to think about it as a measure of speed of particles. And so when you're sitting there in the summer, sipping your iced tea or your lemonade outside in the sun, sunbathing, or maybe hopefully in a week or two when we have our first 80-degree day, I'm being very optimistic, you can go, you know, good thing for that Miss Carosa. She taught me that all the molecules are moving really fast today. Okay, moving on, the next thing we're going to do is convert temperatures, and this is not something that's new for you. We're going to keep our conversions between Celsius and Kelvin. The Celsius and Fahrenheit are just totally, you know, they're weird. We don't need you to memorize those equations. We'll always give them to you. But you should know pretty much inside and out the conversion from Celsius to Kelvin and vice versa. So we'll go through some of those now. Several of the questions in your quiz, and I believe this is a 5-question quiz. It's a short one because there's not much here to really understand. they talk about absolute temperatures. So that's a new term. An absolute, what is the absolute temperature of this or of that? And we want you to know that any temperature expressed in Kelvin is an absolute temperature. So if I convert 0 degrees C to Kelvin, I'm adding 273. 273 K is an absolute temperature. So is 373 K and 273 K and 0 K. They're all absolute temperatures. We consider the Kelvin scale to be this absolute scale because it's the one that we use to compare absolute zero to. And this graphic is another sort of showing you where water boils and water freezes and all of that. But you guys know these temperature conversions. They are not new to you. Plus 273 to go to Kelvin. We should always remember Kelvin is the bigger of the two measurements. They're always in the hundreds, right? 1, 2, 300 temperatures. And then Celsius are small numbers. Very rarely do you get a number or a measurement above 100 degrees Celsius. Okay, so a couple examples, and then we'll wrap up. So I'm going to ask you to log this after I'm done reading it into the, on the sidebar there. At 82 degrees C, the pressure inside a gas-filled container is 567 kilopascals. What is the absolute temperature of the gas? 82 C minus 191 K or 355 K. Awesome. Remember, absolute temperature, you should automatically think to yourself, that is equal to degrees Kelvin. And we don't write degrees when we do Kelvin. We do write degrees C, degrees F, but there is no degrees when we do Kelvin. We just write K. Okay, so absolute temperature has nothing to do with the pressure. We don't care about the pressure. That's just extraneous information in there. Meant to throw you off? Maybe, maybe not. It's a scenario. If you're a scientist, you need to make observations of the situation. Perhaps you're taking the pressure and the temperature of a system. You notice it's in degrees Celsius. No thermometer measures in Kelvin, so you're always having to convert to Kelvin. The only number you're really concerned with here is 82 degrees C. And all you need to do is convert that to Kelvin. 82 plus 273 is 355. Okay? We would not answer 82 because that's the temperature that's in the problem. It's not Kelvinized. It's just Celsius. And then, I don't know what, minus 191 I think is if you accidentally subtracted and used the other. In this case, you would add 273. Okay, so now that you're sure you know how to do problems like this, I'll give you another shot. Maybe redeem yourself if you weren't right on the first time. Question says you have 0.4 liters of air at a pressure of 190 kilopascals and minus 50 degrees C in a rigid sealed container. What is the absolute temperature of the air? Minus 50 C, 223 K, or minus 273 K? Okay, again, absolute temperature. You're given a lot of information here you could work with. Perhaps, I mean, maybe you would be solving for N in the ideal gas law, right? You're given volume, 0.4 liters. You're given pressure, 190 kilopascals. And you're given temperature, 50 degrees C. From what I can tell, all you need is gas constant R. Pick which one you're going to use from kilopascals, right? I think that's the 8.3. And you can solve for N. But that's not what the problem's asking us for. It says, what's the absolute temperature? Absolute means K. So we take this minus 50, and that's all we're interested in. We go ahead and we cross out the 50 that's available there, because minus 50C is minus 50C. It's not Kelvinized. We want to go ahead and add 273 to 50. And we get 323. Oh wait, minus 50. Wait a minute. See, you gotta be careful. Minus 50. So your answer then is 223. Okay. Okay. B. Pretty straightforward. I think there's 3 or 4 of these problems on your quiz. So if you need to, rewind this video, watch those again, solving. Absolute means temperature in Kelvin, and that's all you need to know from this lesson, along with how molecules move at different temperatures. There's also this question on your quiz, and it's the exact quiz question. I typically don't like to do this, but I am because I know we're not the strongest at reading graphs, and in the course in general, we don't spend a great deal of time trying to teach you how to read graphs. So I'm going to take some time here and break this down for you, okay? This says, in the diagram at left, gas A and gas B are at the same temperature and volume. So we're not necessarily talking about changes. We're not looking at gas laws. We have number of molecules listed on the y-axis. So what that means is that at the top of this axis we have lots of molecules, and at the bottom we have few, if any, molecules. All right. Now on the x-axis we're looking at speed. That means at the top end of this axis, we have fast molecules. Whoops. And at the bottom end, we have slow molecules. Okay, but we're primarily interested in the graph itself. It says which gas is at a higher temperature, A or B? Well, I don't know, Mrs. Crosis. There's no temperatures listed there. How am I supposed to know this? This brings us back to this idea that I didn't clarify yet, and that is average kinetic energy. Whenever we have an average anything, it's considering the top end and the low end. Average weight for your height takes into consideration everyone at your height, whether they're 400 pounds or 40 pounds, right? And they average them together. The result is always what we call a bell curve. When you get to college, you'll hear about this a lot because a chem test may not be 100 is an A or 90 to 100 is an A. It could be like a 60 to 70 is an A because that's where most, C. Wait a minute. Generally, we set a grade level C between a 70 and an 80. But in college, and particularly different classes, I actually took a class in college. It was called physical chemistry. It was part 2. It was incredibly difficult, and I did very badly in it. Where the average was a 40. Average. C is considered average. It's in the middle, right? It's not a D or an F. It's not an A or a B. It's right in the middle. So 40 was an average. 50 was a B, and 60 was an A. Can you imagine getting a 60 and having it be an A? Because if he failed everybody that got under 60, the whole class would have failed. So sometimes this happens in college. In any case, it's an average. So what we have in the blue graph here shows us that most of the molecules at the peak, that's the area where we have the most. That is the average. Okay? There's some that are higher speed, if we look at the x-axis. There are some that are lower speed, but this right here is where the speed of the A molecules are. The speed of the B molecules would be at the peak of that curve. Okay? So if you're comparing speed, you would be comparing them to these points on the graph. Now, we can also compare them against number of molecules. How many molecules are there? And if we do that, we take that same peak and we draw it across to the y-axis. So A has that many molecules and B has this many molecules. Okay, so now I want you to take a pause and try to answer the question. Which gas, according to the graph, is at a higher temperature? Is it gas A, right here, because there are more molecules? Is it gas A because the molecules are moving faster? Is it gas B because there are more molecules? Or is it gas B because the molecules are moving faster? Okay, the correct answer here is it is gas B because the molecules are moving faster. So if you answered that, yay for you, way to go. Again, we say here we have the peak showing up here, and if we draw it to the x-axis, we're closer to fast molecules than A is. A is more toward that slow side. So comparing speed, we're saying B is more. Now we have learned today that high temperatures equal fast molecules. So that's something that we also need to know by definition. It has nothing to do with the number of molecules at all, temperature. Temperature is all about speed. Okay, why is all of this relevant? Why do we care? What are scientists doing? Scientists are producing magnets that can levitate. And of course that means to be held up above a surface with seemingly nothing. So they can make what's called superconducting magnets. And I might talk about in here what their application is in terms of why do they do it. It says here their electrical resistance disappears. So there's some, let's see, particle accelerators that use these. I don't really know what the application would be, but it's cool. You wouldn't believe the amount of science that's done and the government pays for that is just simply cool. And probably they learned something from, but it has no practical application in the world. Someday it will. That wraps up lesson 11, absolute zero. We have absolutely gone through each of these ideas. We've described the relationship between kinetic energy and temperature, and we have practiced converting some of those temperatures. We are done with Monday. Hopefully you watched that recording yesterday, so hopefully you have that done. Big check. And today you need to complete your 1.11 quiz. And as I said, I think there are only 5 questions there. So nothing too heavy today. And that's all I have for you. So tomorrow we will have an installment of lesson 112, which is Dalton's Law of Partial Pressures. I hope you're having a good week. Wednesday gets us halfway there. And do take note, we do have a test coming up on Friday. So somewhere in here will also be our review. Have a great one.